okay? All right. Set this one over here so we get feedback. John, thank you for the warm introduction. Mickey, thank you. Where's Mickey? Mickey, thank you for taking such good care of us. Talk louder. How about now? Better? Okay. Thanks for taking such good care of us. It is an honor to be here. You know, I was born in Harrison. Some of my absolute fondest memories are of coming up here to visit my grandparents and my cousins. We always live far away. I'll talk about that in a minute. But an opportunity to come back and share some of the adventure I've had really is a treat. And when I talked to the kids at Valley Springs this morning, I tried to drive that home, and I did a fun little thing. We'll do it here too. So how many people have been born within 50 miles of where we're standing right now? All right. So, okay. And then how many people have one or more cousins in the room? And, you know, so I got them on that one too. They didn't see that one coming, but I did. So I'm going to share a little bit of my story with you. It is a story about great achievements and daring and failing sometimes. I'm going to show you some of the warts too. Not everything always went the way we wanted to, but if you're not familiar with Kennedy's speech at Rice, where he says we choose to go to the moon not because it is easy, but because it is hard. That speaks specifically to me, but the challenge of doing hard things is what makes America great, right? You do hard things and you don't know if you can succeed at them or not. And in the attempt, you make yourself better, you make your community better. And that's been my experience. So before I go on, I gotta say one more thing. I want to thank my mom. So we mentioned that. All right, so here we go. How do you get to the moon from the Ozarks? Well, this is my Indiana Jones map. We started in Harrison in 1973. By the way, I was born in January of 1973. Apollo 17 was in December of 1972. We had never landed an American spacecraft on the moon in my lifetime until 2024. And that's something I love hitting the reset button on every time we go. My dad was in sales, so we moved to Little Rock. We moved back to Harrison. We moved to Little Rock, moved back to Harrison. Sometimes he was doing sales. Sometimes he was a truck driver. So he did what he had to do to support his family. Then he got a job in sales in Baton Rouge, Louisiana. And there I am in a Peterbilt t-shirt. With my baby sister off to the side, but I propped her up. Ended up in Monroe, Louisiana for a while, then over in Bossier City. Bossier City, right next to Shreveport, is the home of Barksdale Air Force Base. One of the things about Barksdale Air Force Base that's interesting, they have a very, very long runway because that's where the B-52s take off. It used to be home of the Strategic Air Command. It's one of 2 or 3 runways in the United States that the space shuttle can land on when it's on the back of a 747. Well, my dad's office happened to be at the very end of that runway. And when I was about 10 years old, I was already a big fan of science fiction and Star Wars and all that stuff. But the space shuttle was coming to Bossier City. And my dad took me to the roof of his office, and the space shuttle flew right over us and landed. And that set the hook in a way that I never quite got over. Well, probably around 83, 84, we moved to East Texas, a town called Lufkin. I was terrified. Those Texas people are crazy. Everybody knows them. And I don't know what we're getting into, but there we are. And we stayed there for a while. I ended up playing a little bit of football. Then I did go to a small engineering college in Austin for about 10 years. I was recruited to play at Arkansas, by the way, and very nearly ended up in Fayetteville. But Texas had a secret weapon, and my lovely wife Melissa was a year older than me, already a PhD, and so I had to go there. And then in 2000, we made it to the Johnson Space Center. There, I was a member of a fantastic team. I like to say I worked in the Advanced Mission Design group. So I worked in the best group in the Aeroscience and Flight Mechanics division. I was in the best group in the best division at the best center for the best agency of the best country in the world. I'm pretty sure I had the best job of anybody. And I loved it there. Worked at the Johnson Space Center. Started out working on Mars Science Laboratory, And my job was a guidance, navigation, and control engineer. And so what's guidance, navigation, and control? If you're familiar with the Tesla self-driving car, the computers in the Tesla take the information from all the cameras and the radar and compare it to maps, and then put that into software and decide what to do, and then turn the wheel and move the brakes. All of that system for a self-driving car, if you then take that same kind of need and capability for a spacecraft, how am I pointed, where am I going, am I moving fast enough, do I need to fire the thrusters? That was my job. And so I worked on the entry system for the Mars Science Laboratory. Their recruiting pitch, by the way, in 2000 was come to Johnson Space Center to real-land humans on Mars in 2005. And I saw, let's do that. Didn't quite work out that way. I also worked on a project called the Hubble Robotic Servicing Mission. You recall we lost the Columbia Space Shuttle in 2003. And there was a mission on the books to go repair some issues and replace some sensors on the Hubble Space Telescope. They had done this many times in previous shuttle missions. The problem is the Hubble is in a different orbit than the space station. And after Columbia, they didn't want to fly the space station, space shuttle, anywhere but to the space station, because if they had a problem going up, they could safely keep their crew on the space station. But if you went to where Hubble was and you had a problem, it was too far away. You didn't have enough fuel to fly over to the space station and be safe. So they worried about it a lot. And for a few years, we worked on basically a robotic vehicle to go up and grab Hubble and then have all the equipment and robotics to go and repair it and update it without having to send people. We ended up not doing that project because they did get comfortable with the space shuttle doing one last mission. In fact, there's some great pictures online of 2 space shuttles sitting on the launch pad because they had a rescue space shuttle ready to go in case there was an issue. And then I worked on the Orion spacecraft. I wrote some of the first requirements for the Orion spacecraft. We called it Apollo on steroids. We were going back to the moon with people in 2012. All right, here we go again. And we worked on that for a few years. It started after about 10 years at the agency. It started to weigh on me a little bit that I was working on programs that took decades, and it took a long time to do them. And I was growing impatient. And so I came to kind of a crossroads, and along came Morpheus. And Morpheus was a program established by Steve Altimus, who was the director of the engineering division at the Johnson Space Center. He's also my business partner now, helped found Intuitive Machines. He also was frustrated at the pace that it was taking us to do things at NASA, right? And he said, what if we could do things faster? What if we could develop and learn and fail and try again? What would that look like? And so we put together the Morpheus project. That vehicle, as you can see, it's about the size of like a VW van. Each of those spheres are 4 feet across. They're aluminum fuel tanks. 2 of them hold liquid oxygen at negative 270 degrees Fahrenheit. The other 2 hold liquid methane at negative 280 degrees Fahrenheit. It's what's called a cryogenic propulsion engine. No one had built an engine like this before. Go build this new engine. The engine is 3D printed, by the way. So it's made out of metal, put into a 3D printer. New technology. Can we make it work? Also, we want you to find a way to control it autonomously, so you don't have to have people steering it. We want all the software on board to steer it. Can we do that? By the way, I want it done in 9 months. I don't know if that's going to work. It's going to work. And the rules are, you go as fast as you can, and if you blow it up, get your clipboards out, stand around the smoking crater, take notes about what didn't work, and build another one. So, all right, I'm on board. Here we go. So I'm going to walk you through some movies, and we're going to see how well this whole thing worked out. And I'm here, so it worked out pretty good. Perfect. All right, so the first thing we did was we did what was called tether tests. And the idea was, as we're learning, let's get a 100-ton crane, fill this thing up on the ground, lift it up, and let's just see if we can make it hover. Baby steps. Let's make it hover a little bit. And then if something goes wrong, we hit the kill switch and and we'll go. Okay, so first thing we said we would do is we're going to do that. 43.
TFC, contact. Contact. Clear, contact.
More hair and darker. First test was April 25th, and we just tested the engine. Wasn't enough thrust to lift the vehicle up, but everything looked really, really good. So we refueled it, went back out 2 days later, and what could go wrong? That's a 2-ton tetherball. And we proved that the manual abort switch could be activated in less than 13 seconds. We thought it was 15 seconds. And so it worked out pretty good. I wore my brown pants that day. It was actually, it was a triple error, and it saved the vehicle. So the first error was, we had these bungee cords on the top that were supposed to pull the tether away so it didn't hit the top of the vehicle. And the rigging crew was so excited about it that they tightened those bungee cords. And one side was way tighter than the other. So the vehicle came up and immediately pitched over to the side. The other error was we underestimated how much power the propulsion system was going to pull in its control circuit. And it fused shut at 105% throttle. So my software, which is telling it how to fly, is going, you know, slow down, slow down, slow down. It's just like me talking to Melissa when we're going down the interstate. You know, slow down, slow down, slow down. But there were no brakes. And so it didn't matter what commands the computer was sending, the engine was stuck wide open and was not going to stop. The third error was there's a unit which tells the vehicle how it's tilted, and it had been installed twisted 90 degrees. And so what should happen is if the vehicle goes this way, the engine should go to the high side to correct it back. And instead, when the vehicle went this way, it went 90 degrees to that, and that's why you see that corkscrew. But if we hadn't had that corkscrew, because the engine was stuck wide open, it would have gone straight through the top of that crane and dragged this thing towards the middle school. It's about a half a mile that way. Would not have been in good shape. So this is April 27th, 2011. About a week later. Better. Not quite there yet. Working on it, and I'll show you the progression here in a minute. But it was unheard of to have a near disaster and then 2 weeks later to do 3 flight tests in a row and get back on the horse and try again. But we had the support of the agency. We were challenged to move fast. We were challenged to try new technology. One of the things I want to share with you about this, this is the most beautiful color blue. I love methane engine exhaust. And at negative 280 degrees enters that engine. And the engine, when you look at it, it looks kind of like a shower head. And there's two chambers inside of it. One has the methane, and it sprays methane jets. The other one has the oxygen, and it sprays the oxygen jets. And it sprays these together to get them fully mixed in the combustion chamber. And the better they're mixed, the more thrust you get. So it goes from negative 280 degrees to 2,500 degrees in about 1.5 inches. That's how much power this engine is releasing, and that's why we're able to fly this big vehicle. But no one had built an engine like that before. So fast forward, and we kind of begin to figure out
5, 4,
how the system should work.
2, 1.
That's simulated Mars dirt as well. We wanted to see how the vehicle would interact with the Mars dust. You see the feather hanging now. It's actually flying, but it looks rock solid. The engine's actually correcting 100 times a second. In the same way you might balance a broom on your fingers and you move it around to keep underneath it, the engine is standing underneath that vehicle to keep it from going side to side. It's doing it so fast and so accurately, it looks like it's not moving, but it is. So we felt pretty confident we had the system worked out. And we said, hey, let's take the tether off. So far, that unit that earlier we had mounted 90 degrees wrong failed a half second after liftoff. And without that, it's like if you had an ear infection and you get dizzy and you don't know how to step, the vehicle didn't know how to correct its tilt. And so it came all the way over. And this is at the Kennedy Space Center. That's a simulated Mars field. And the vehicle, that's hot gas escaping from the tanks. It makes this horrible, horrible puppy sound. It's just, it was tragic. And you're sitting there going, man, this can't get any worse. Usually when you say that, things get a little worse. We're about 1.5 miles away in a command center. And I'm watching this on TV, and we called the local fire department. Ooh, there you go. Got worse. They got another view of this, and each of those tanks weighs about 500 pounds, and it blew that tank about 100 yards away when it went. That's the other view. We had to walk that in kind of a survivor's grid later, pick up and tag all the pieces, and I'll never get the smell of burnt lander out of my nose. But we loaded up, and it turns out when we did this, remember, our charter was you go fast, and if you blow it up, that's okay. That was the first vehicle. We had what we call the Bravo vehicle, about 70% complete. We'd already been building the replacement vehicle because this was an acceptable test condition for us. And so a few months later, we come out and we reloaded. That landing area is about 2 football fields. It's about 100 yards by 100 yards. Better. So the last trip in this program, we were supposed to not only do that, we were supposed to do it at night. And so we had to show that our system would work in the dark, because I'll show you the south pole of the moon in a minute. It's dark on the south pole of the moon. That's the runway where the land space shuttle entered. You see little flashes on the side of the land from time to time? That's the side jets controlling its roll. But the pitch and yaw are going in operating engine. Now the thing you see in the top left corner, that's the laser that we use to scan for signals. It's about the size of a microwave. The whole thing sits out on the side. It's looking for the same place to look. So we felt pretty good. Yeah. All the test objectives were made. The project was a great success. Like I said, we love what you guys did. Now go back to your desk job. That didn't work for me. So we founded IN in 2013. And we're really motivated not by a single widget, not by just the engine or the automation technology, but we really knew how to solve problems in human spaceflight. From Apollo 13 to today. In fact, I just heard today, they're rolling the Artemis spacecraft back out to the pad. They fixed the issue. They're going to launch in April. Really good at solving problems. So what if we went out and we solved problems using the way we do engineering for aerospace, energy, and medicine? And we were a think tank for about 5 years doing that. We had close to 30 inventions. We had 5 or 6 companies that we spun out. We didn't fall in love with any of them. There was some cool stuff. We invented the Tiburon drone, Tiburon Spanish for shark. It was a surveillance drone that had enough endurance that it could fly from Harrison, Arkansas to Paris, France, not Paris, Texas, Paris, France, on a single tank of gas. We flew it in Antarctica, first drone to fly in Antarctica. We developed a suicide prevention system. This did kind of use lasers. There was a clinic in Houston that was having a rash of suicides, their psychiatric clinic, and they wanted help being able to detect when somebody was tying something around their throat or standing underneath a door where they might hang themselves or something like that. They didn't want to invade their privacy and look at them with cameras. So we used a laser system to take a silhouette image, and this computer would tell the nurse's station, this person is doing something that may harm themselves. So we invented that. We invented a device to automatically put an IV in your arm. If you've ever been stuck multiple times trying to get an IV, that's not pleasant. So we invented one of those. And we worked in oil and gas quite a bit. This is a capping stack. So remember Deepwater Horizon, where they had the big blowout in the Gulf? Halliburton and several other companies invented this device, which is called a capping stack. And they would take it out in a big ship, and if you had a blowout, they would drop the capping stack and put it on top of the blowout, clamp it down, and then use that as a valve to seal it. And they came and talked to us because this looked to us a lot like a rocket engine turned upside down. You had high pressure gas coming out of a blown out well. So we did a lot of different things. It was good work. We were always, if you ran into me at the airport, I'd always go, so what do you do? And whatever in car seats, really, what are your car seat problems? Always looking for problems, trying to help solve what people were doing. But in 2018, NASA came out with the Commercial Lunar Payload Services Program. And this is an evolution of where NASA has been over the last 20 years. So at the end of the Space Shuttle program, NASA moved to commercial crew services. So NASA no longer flies astronauts to the space station. They hire SpaceX to do it, or they hire Boeing to do it. And they write a contract very similar to what you do when you purchase an airline ticket. And they'll ask SpaceX, hey, I need you to take this much cargo, this many crew, it needs to be there in October. And NASA got very comfortable that that model worked effectively and was more cost effective than NASA maintaining their own fleet of spacecraft. If you fly Southwest Airlines, it's Southwest Airlines that's doing that transportation. Nobody flies a government plane outside the military. So they were moving in the same direction. They said, look, let's try this for the moon as well. And so the Commercial Lunar Payload Services is a lot like FedEx or UPS, where NASA will come out and say, we've got a number of payloads, we'd like to go to a certain space on the moon. And then there are 14 qualified bidders in the CLIPS program. We'll write a proposal and a competitive bid and go, I'll take your 14 payloads, I'll launch them on my lander, we'll do all the things. So we applied to the program, we were accepted. We wrote to ship on the first task order, we were accepted. There's one problem. I was a company of 40 people, I didn't have a lander. What are we going to do? Well, it turns out about half of our company came from the Morpheus project. So when we left, the guidance engineer came with us. The software engineer came with us. We hired the propulsion engineer when we started working on this. So we reconstituted a lot of that team, and we brought them in, and we said, Laura, if we're going to build a lander, what's the first thing you need to do? Got to build an engine. We got an engine guy. Great. Where are we going to test it? You test it in a big building. I don't have a big building. So what do you do if you don't have a big building? You get a flatbed truck. We spent $13,000 and we bought a flatbed truck with 300,000 miles on it. And these nerds all come walking out of our office building, and the guy driving the truck comes up and stops, gets out and looks at us, and we're not the usual clientele when he delivers a flatbed truck. And he goes, what are you boys going to do with this truck? We're going to put a rocket on it. He kind of laughs. No, really. Not really. Pauses and he goes, I'll see you on YouTube. He wasn't quite sure what was going to go on. But sure enough, a few months later, we're up and running, and we have built the next generation of that engine. We're putting it through its paces. A standard day for us would be to get up at 6 o'clock, load this truck and a command trailer up, drive out through the NASA gate, through another gate, through the Ellington Airport gate, and go to an abandoned taxiway with registry, spend 4 hours packing everything back up to make sure it wasn't leaking, test for 8 hours, disconnect everything.
Send automated
Don't want to see that again. Drive back in, and for about a 16-hour day, we get about 6 hours of testing. Over and over and over again, trying to perfect this engine technology. By the way, the other 13 companies that were all in the pool, none of them used an advanced propulsion technology. They all used the standard propulsion technology that everyone said you should always use. So every time somebody would write a proposal, we would write, trust us, it'll work. And they would write, don't trust them, it'll never work. Competitive disadvantage. The other interesting thing about the CLIPS program is, it was what they call turnkey. NASA wasn't going to provide communications. NASA wasn't going to provide tracking data. NASA wasn't going to provide the launch service. NASA wasn't going to provide the ops center. So we had to build our own operations center. That's node of control. Landed 2 missions to the moon from there. And because we weren't able to use the NASA dishes, we went around the world and we found dishes anywhere from 40 to 90 feet across that were being used for astronomy. And we found something very interesting. If you're doing astronomy, you don't like the moon to be in the sky when you're doing it. Because the moon, it turns out, is very, very hot. And those dishes are looking for things that are very, very cold. So to them, when the moon was in view, it was garbage time. For us, I want to use your dish to point at the moon because I'm at the moon. So we're able to strike a deal with a number of these stations, and we made the first commercial ground network able to communicate to the moon. How big a deal is that? The moon's about 250,000 miles from Earth, which means you have to use 400 times more power to talk to something at the moon than you do something at Earth orbit. So you need the big dishes in order to communicate. And then we started building the Nova C lander. First one flew in February of 24. Second one flew in February of 25, landed in March. And then we're going to launch another one at the end of this year, IM-3, and then IM-4 goes up late next year. Why Nova C? Nova is Latin for new. It was a new start at exploring the moon, and C is the Roman numeral for 100. We designed it originally to try to deliver 100 kilograms to the lunar surface. We overachieved a little bit. We can do about 140, so it's got a little bit more punch in it than that. The engine works a lot better than we thought it did. It's roughly a hexagonal shape. It's about the size, I don't know, it's about 20 feet tall on top of the landing gear. It's about the size of an old school phone booth. It's pretty big. The inside is completely hollow. There's two large tanks on the inside that hold the liquid methane and the liquid oxygen. And then on the outside, we have these gold cover tanks. Those contain helium as our pressure. So we push the propellant through the tanks using high pressure helium, the same way that the CO2 canisters push the soda water through at the gas station or at the movies. We just use helium because it's better for the prop system. Columbia Sports Apparel saw our spacecraft on our design idea on the internet, and they said, "Man, your gold tank looks a lot like their OmniShield gold material that they were putting in all their jackets." And so they said, "Can we kind of do a NASCAR style sponsorship and give you, all the mission control shirts? So we have quarter zips that we wear." They did a whole marketing campaign. We said, sure, why not? And we could do that because this isn't a NASA mission. It's an Intuitive Machines mission that NASA is one of the customers. In fact, NASA wanted it that way. They said, we don't want to be the only customer. That's too expensive. We want to be one of many customers. So on our first mission to the moon, we had 5 NASA payloads, and we had 6 payloads that we went out and found for people who wanted to go do lunar stuff that weren't NASA at all. So it was a great partnership, and I'll tell you, we found out that they had a pretty good toolbox too. In space, we do a lot of work to make sure something works really, really well at once. In the clothing industry, they have to make sure it works well 14 million times. Because if their material goes out and makes somebody sick, there's going to be a real problem. Their chemists were really good, and we found out the material they were using is actually really, really good at space. And that's now critical on all our missions. We have Columbia Sportswear insulation that protects that negative 280-degree propulsion system. So those are 2 of my metal babies. The one on the left is Odysseus. We called him lovingly Odie. So we flew Odie first, and then that's Athena on the right, Addie, as we call her. And we're not married to the Greek names. Our third mission is going to be Trinity. It's the third one. The Trinity test site was very energetic. I could use a little divine help, so we're going all the way through. But those are our 2 birds, and that's where they're getting encapsulated. So the dark gray stuff you see on either side, that's the top part of the Falcon 9. So we take it down to the Cape, and they bring these 2 pieces. It's called encapsulation. They bring that in, bolt all that up, and they roll that out to the pad and put us on top. Our trajectory to the moon looks a lot like the way they did in Apollo. So we launch on the SpaceX rocket, and it basically is like getting shot out of a cannon. 30 minutes after launch, we separate, they let us go, and we're on our way to the moon. After that, we have to do a number of trajectory correction maneuvers in here. And if you play golf, you know that you drive, and then you're going to have to putt. So for us, those trajectory correction maneuvers are like a putt. We travel about 1 million kilometers to get to the moon because we go up, we circle it a few times, and then we land. And we hit that as accurately as we can. Once we get to the moon, we have to do about a 10-minute braking maneuver. If we don't do that braking maneuver, we'll slingshot past the moon and we'll go off into the solar system. So we get there really fast, and because we have the most powerful engine in the fleet, we're able to stomp on the brakes and stay there when we get there. We spend some time in lunar orbit, and then we do what's called power descent. The engines come on for the last time. They're going to burn for about 15 minutes. We're moving at about a mile per second when we're in lunar orbit. We have to go from moving a mile per second to 0, and that's what the engine allows us to do. When we start out, if we're moving from this side to the left to the right, the engine points in the direction we're moving because we're braking. It's slowing us down, trying to fire in the other direction. And then as we get closer to the landing site, we start to pitch over, and then we take a picture of the landing site, and we use that to determine where the safe spot is, just like we did on Morpheus. And then we brake, and about 100 feet over the landing site, we come down safely. A very important part of this is the laser that we use to measure how far above the surface we are. We've had problems with that on our first two missions that we're working on to solve right now. I'll explain that in a minute. That's another view. So I mentioned that braking. This is us coming in and then coming down. These fish bones you see, that's the thrust vector. So this shows you that I'm thrusting in that direction. And the size of the thrust vector tells you how much thrust it is. So thrusting hard, then when we pitch over, we're not thrusting as much because we want to stay level. So we have to thrust equal to the weight of the spacecraft. And we're throwing out propellant as we're thrusting. So the spacecraft's getting lighter and lighter and lighter, which means we have to thrust less and less and less and less and less. So the technology of our engine allows us to basically throttle it down as we land. There's us coming off of the SpaceX rocket. It was a great launch. It was a little bit nerve-wracking because no one had launched liquid methane and liquid oxygen on a SpaceX rocket before, first time. It worked great. Melissa was next to me watching the launch and giggling the whole time, and I wasn't breathing. We finally get up. They kick the vehicle off. One of those feet, by the way, has the name of everybody in the company at that time stenciled into it. And so we took that to the moon as a memento for them. This mission landed at 80 degrees south latitude. The previous southernmost landing had been the Indians who'd landed at 7 degrees south. And it's funny because the Chinese had landed at 60 degrees south and said, we've landed on the South Pole. 60, that's not the South Pole. That's like Greenland. And then the Indians landed at 70 degrees. No, we landed at the South Pole. It's like Iceland. It's not. So we landed at 80 degrees. And of course, you know, we said, we have landed at the South Pole. And so this mission is headed to 80 degrees south from the moon. When you look at the moon at night, if you look at the very bottom of it, when it's at a half moon, right where the shadow hits, that's where this lander is right now. Okay, so kicked off. Man, it's great. I go home. What could go wrong? Everything. And about 4 hours later, I get a phone call. You need to come back up here. We have a camera on board that takes a picture of the stars. And it uses that picture of the stars to figure out how we're pointed. You know what star you're looking at. You know which way you're oriented. And we need that in order to turn our solar arrays to the sun to charge the batteries. Well, we got pushed off the vehicle, and there was a bug that was preventing the camera picture of the stars from getting to the computer. So the vehicle was in this slow tumble, and there's the SpaceX rocket that we've kicked off of. There's the sun. We're looking down at the engine here. There's the landing gear. We didn't put any solar arrays on the bottom of the vehicle because they're never going to see the sun. Except that's the side of the vehicle that's seeing the sun now. And the batteries aren't charging. And we're running out of power. So we had to come in and figure out how to do a patch. We'd never practiced patching the software on the ground. And so the first time we patched the software on the vehicle was when we were in space, and the vehicle had about 3 hours before the batteries died. So we fixed that, got that out of the way, battery started charging, I go home. Gonna be an easy day, not a problem. Phone rings. You need to come back up here. So we planned on getting into an orbit that was about 60 miles by 60 miles at the moon. And it's 100 kilometers by 100 kilometers. I was on the shift where we did the capture maneuver, where we got into lunar orbit, and we thought we were about 90 by 75. So not exactly what we wanted, but good enough. We're basically in orbit. Everything looks pretty good. We watched it for a day. I go home, literally put my leg in the bed, phone rings, you gotta get up here. We weren't in a 100 by 100. We were in a 150 by -1. Now, if you're not a pilot, -1 kilometers altitude is not good. You do not want to do that. And so we raced back up there, and we had a maneuver loaded up to raise the altitude, but we weren't in a good position to do it. And when we came around the moon at that -1, we were right here. This is a topographical map. If it's black, it's at a low point, and if it's red or yellow, it's at a high point. And the moon, because it has 1/6 the gravity of Earth, it actually has higher mountains than Earth and deeper valleys than Earth. It's about 3 times what you get from the tallest Earth mountain to the bottom of the ocean floor is where you are at the moon. So when we flew through this one part, we were about a kilometer and a half below the average surface of the moon, and we flew through a valley. A little bit of providence, a little bit of luck. We took a picture as we went through, and sure enough, we saw a crater on either side of us as we were flying through the bottom of that crater. So we fixed that, and then we landed. We found out that we had a cable problem on our laser, and the cable prevented the laser from giving measurements about how high we were. So remember that sequence where we go and then we pitch over and we come down? We contacted before we completely got where we were going straight up and down. We were still going sideways a little bit. And our desired trajectory would have been along this blue line and landing there, and we ended up landing early right here on the edge of this crater. The crater doesn't have a name, but I like to call it Penelope, because Odysseus was making his way home. And this is a picture we took. We landed too fast for the landing gear, by the way, so the landing gear snapped, and we ended up on our side, but the vehicle was fine. We operated for 8 days on the lunar surface. Got some great scientific data. And the thing I like about this picture is, this is looking down this slope into that crater. The crater's about 1 billion years old. So we're looking down, and then you can see this light area up here. That's the far side of the crater. So that really brought home to us what we had done. Oh yeah, and this is about where we hit, by the way. So you can see we hadn't quite gotten where we were in the up and down part, and we hit a little bit early. Remember, it started like this. So we were pleased with the progress we made. We had a lot of firsts. No one had fired an engine like this in space before. So there were a lot of questions about whether the technology would even work in a vacuum. We proved that it did. There were a lot of questions about could you use non-NASA ground tracking and communication assets. We proved that you could. There were a lot of questions about could you build a spacecraft for as cheap as we built it. We also proved that. We had 75 improvements that we identified. If you want to learn how to do a thing, do it once. If you want to perfect it, you do it again. So we identified 75 things that we needed to improve, and this list, which I won't go through, don't worry. This list were the ones that were either mission threatening or mission critical on the first one. Let's go fix all of these things on the next mission. So a year later, we load up for IM-2, and very similar trajectory. We tweaked a few things. When we separate from the Falcon 9 rocket, you'll notice these 2 bright points. We actually had customers who wanted to just tag along. And they sat underneath us on the rocket and then ejected after we ejected, and so we took a picture of them as they went on. And you'll see that in the video in a minute. This is super nerdy. I shouldn't have put this in here, but basically this shows you that we didn't hit the moon, because our solution for tracking was here, and this was the solution for tracking that NASA got using their data, and they were very, very close. So that 150 to -1, we nailed that problem with that flat. Since that's what I studied in college, I always put that in one of my charts. Okay. So there's the launch, and we included some better cameras on this one. If I can make this guy work. So you can kind of see, when we first come off, you can see those little spacecraft eject. Pretty good shots of that. There's another one. So there's a couple little bump outs. You see that? That's a spacecraft satellite right there. We had 3 of them on board. And if you look closely when I play this, you'll be able to see those guys fly off. There you go. pretty good pictures of the Earth on the way out. We get to the moon, the engine has to burn, just like on Morpheus, has to burn for about 10 minutes to capture the orbit. So this is a video during that burn. It's smooth. Right? The vehicle's doing great. Having worked on Morpheus, I can almost hear the roar of the engine every time I see this. You can't hear it in space because in a vacuum there's no sound. But I hear it. That might be PTSD, but I hear it. So we've got some great shots of lunar orbit insertion. I like this one because you have the Earth up in the corner. When we did this maneuver, we're actually coming around the north side of the moon to south. So we've been top to bottom. And as we first came around, you could actually see the Earth from the camera. And you can see it wiggle around as the vehicle's steering through that burn. Same thing from another camera that's looking at the sun as we're coming down. Moon's a very harsh environment. On the sunward side, it's about 240 degrees F. And on the shadowed side, it's about negative 200 degrees F. And then if you happen to be flying over the moon where you have the sun on one side and the moon below you on the other side, you're actually getting baked on both sides. So you go from these extreme hot periods. If any of you guys have ever been out at the lake, you got your hat on, you still get sunburned, that reflected sunlight, it bakes the spacecraft too. It's very bright, very hot. All right, so now we're in lunar orbit. We got to about 97, about 85. That's not because we missed our target. We adjusted as we went out to correct some errors, and it was good enough for us to do. So great pictures. I love watching the reflection of the moon in some of the shiny surfaces on the lander as we go through. And to give you a sense of scale, my chief scientist put some of these together. So this, there's a Crain crater, that's about 3 miles across right there. This G crater, that's Gibbs, that's 79 kilometers, so that's like 48 miles across. Big place, the moon. And now, why did we do all that night testing with Morpheus? Well, this is what the South Pole looks like in the moon. And we want to land there. So we show this to the scientists, and scientists who want to go find new things and go to places that are scary to go to, they all go, ooh. The engineers that actually have to land there, we all go, hey. It's not really our favorite place. All the systems are checked out. It really is a breeze. You come in, you punch your clock. What are you doing today? We're doing a maneuver. Okay, you do a maneuver, you eat your sandwich, you go home, everything's working great. What could go wrong? Well, it turns out we fixed the laser cable, but the detector on the laser from our vendor doesn't operate properly when it's hot. And because we were doing things cheaper than NASA had done it, we had to put it through all of the testing that NASA would have, and we didn't test it in a very hot condition. So here we are after a near perfect mission on the second try, and again, we don't have a laser. And so we went down and landed, and we landed a little bit too early. But this is what the approach to landing looks like. Those are two cameras playing side by side. Pitch over right about there. So we went through the whole sequence successfully. Everything worked except for the laser. This is a view right before we touch down. So we're about 6 feet off the surface. You can see the shadow of the legs. You can see a little bit of a shadow from the engine exhaust. It's kind of diffusing the sunlight behind us. This is the top-down view, kind of like you get in some of the newer cars, taking all the cameras together. And then there's two craters here at the top, and one of those craters, we're flying this way. These 2 feet are going to hit that crater going about 60 miles an hour. We think we're higher than we are because we don't have our laser sensors working. So in the press, we go, oh, Intuitive Machines lander tipped over. That's a very kind word. You know, we stumbled like Chevy Chase going up on stage. It was a real acrobatic thing. But the vehicle survived. And some of the images we took, that is the closest image anyone has ever taken of the South Pole of the moon. This is at 85 degrees south. That really is the South Pole. That's inside the Arctic Circle, if you will. So we took this picture. Each pixel there is about 1 millimeter across. And this looks to me, I'm not a scientist, I'm an engineer, It looks to me the way sand looks on a beach when it's raining. And you just see it kind of pop up little places. So the scientists, they're all drooling over these images because no one had taken pictures around the moon like this before. Just for fun, we did a little bit of a comparison of how the two missions did. And so in green, you see scoring for IM-1. And in blue, you see scoring for IM-2. And these are all the events throughout the mission, from shipping to the Cape, through the launch, the coast, the trajectory corrections, all the way up to approach. Notice I didn't fill in landing here. And then 10 is better than you expected it to work. And 1 is you really don't know what you're doing. It was an abject failure. And what you'll see is on IM-1, we kind of skirted the line of it could go either way the whole time. But on IM-2, well, the whole mission was really a complete success. And so, whereas on IM-1, it felt like we snatched victory from the jaws of defeat, IM-2 was doubly disappointing because we really had felt like we had done everything we had set out to do, and at the very end, it didn't go our way. However, we are undeterred, and we are going to land and stick the landing of IM-3 at the end of the year. By the way, I'm not taking 1 laser with me this time, I'm taking 8. I will never again fly to the moon without a backup laser, which is a kind of cool thing to say. Okay, on the first mission, we ended up landing about 2 kilometers, about 1.5 miles from the landing site. On this one, we ended up about 500 meters away. So even though the system didn't work at the very end, we were still very close. This is a picture that we took. There's that first crater, and then there's where we ended up in the second crater. See it there. We took that image with an American satellite called the Lunar Reconnaissance Orbiter that's at the moon. And the Indians have an orbiter at the moon called Chandrayaan, and they were in a position to take a picture of us after landing. And there's some features here that are kind of cool. Of course, there's Athena in the crater. And you'll see there's a little bit of a dark line here. This is the way we flew in when we were in that horizontal phase. That dark line is the trench that the engine exhaust blew, just like a blowtorch, into the moon. And then from orbit, when you zoom out, you might be able to see it. See, there's a little bit of a white streak. See, it's a little bit wider right there. From that one, you can almost see it. So we uncovered the lunar regolith on the way in. And then, you see those 2 gouges right there? That's where the landing gear hit and blasted the lunar surface out. And we actually did a flip through the first crater before we ended up in the second. We built them tough, but I'm tired of Navy landings, so we're going to stick with next one. So one other thing I wanted to talk to you about on this. This is the picture we took after we landed. And so there's the moon, there's the crater. Here's someone else taking a picture of us in that crater, taking a picture of the Earth. So I landed there. I took that picture. Someone else verified that we had landed there, and they took that picture. They also took these pictures. So, did we land on Apollo 11 and Apollo 12? We absolutely did. The same people took these pictures, and in this one, see these little dark lines up there? Those are the footprints of the astronauts. So, if you're going to believe we didn't land on the moon and we didn't walk around the moon, you have to believe that the Indians took this picture and faked it for us. We started out here. This is our scorecard. So we were very pleased with everything. That last step's a doozy, and we're going to fix it going forward. All right. I'm going to skip this. There's one other thing I wanted to say, though. So, there's a big question about space programming. Why is it important to Americans? Why is it important to you? The days of space being, we're going to go answer the deep questions of the universe, and is there life, and how old is the solar system, and the really scientifically deep questions. Those days are starting to move behind, and we're starting to move to space as a developmental frontier. The Chinese are going to the moon. They are going to put factories on the moon. They are going to go to the asteroids and get rare earth minerals that you can get from the asteroids. So space has gone from kind of being this Yeah, we landed on the moon once, and we go out and we take pictures and we answer scientific questions to valuable real estate. If any of you used a credit card today, the timing on that credit card that allows your transaction to go through works because we have GPS satellites. The weather, of course, but we've really moved out of an era of space being kind of a esoteric, exotic thing that only the big brainy types in college universities care about, to it is the new frontier. It is where we will go. It is where we will develop new resources, and you can't fall behind the Chinese and other countries. So that's the first message I would give you. The second message I would give you is this. There are lots of ways to work in space. You can follow my path with STEM and do science, technology, engineering, and math, the traditional rocket scientist route, and there are great jobs all across the country to work in STEM. You can do business. The engineers are horrible at finances and accounting and all the things that any business needs to run. We have some wonderfully talented people from all walks of life who help us run our business, to do contracts, to have a supply chain, to get insurance, to make sure the facilities are in good shape so the engineers can do their job. You can absolutely be in the space industry working just in the business capacity. The one that's overlooked, the one that's the most important, is skilled technical blue-collar labor. That spacecraft doesn't get built by me. I design it, I think about it, I help write the software, but it's skilled aerospace technicians, plumbers. That whole propulsion system is a fancy plumbing job. We have to have plumbers, we have orbital welders, we have composite technicians, we have electricians, we've got assembly technicians, we've got test technicians. And the trick is, that workforce in the United States looks a lot like me, with gray hair and a limp, getting closer to retirement than the beginning of their career. And we really do need the next generation of skilled workers to kind of follow, the micro dirty jobs, except these aren't dirty jobs, and come have a really good job working as an aerospace technician. In fact, that is so important to us that we partnered with the city of Houston and our local vocational school, San Jacinto Community College, which trains most of the people who go work off in the Gulf and work in the oil field, also trains aerospace technicians now too. And one of the great programs I like to talk about there is their carbon composite technician program. And Logan, one of the young men who worked for us, got out of high school, wasn't able to go to college, didn't know what he was going to do with his life. He's in Galveston working at a surfboard repair shop, putting epoxy in surfboards to fix them. And he hears about this carbon composite technician program at San Jacinto Community College. He goes and gets a 6-month certificate. He's built 2 lunar landers that are on the moon. And that's something he'll be able to tell his kids and his grandkids, and they'll never be able to take it away. So I just want to expand a little bit. Why we're doing this now is different than it was even a few years ago. People who are getting into the space business and space program today, they will see tourism. They will see people paying to have tickets to go to the moon. They'll see factories on the moon. They'll see people bringing things back from the moon. And they'll see people going to Mars. In a way that I would have told you 5 years ago was science fiction. It's absolutely going to happen. And it's a very exciting time to be in the space program. But it's part of a real economy that matters to Americans every day. And you should be proud of the things that everybody from your scientists to your business people to your skilled technicians do to contribute to it. So that's my story. I appreciate your time and I'm happy to answer any questions.
I was just listening this morning to somebody from, was it Starfleet or talking about the Artemis program and the Indians, everybody getting to the South Pole of the moon. And why was that location? Is it because we've explored it before and been there? And they were talking about building. Everybody's in a race to start building stuff up there.
They are.
And who's going to decide that you don't want to take over? I mean, legally, what's the deal? How's everybody going to hash this out?
Yeah, great question. I mentioned we need business people and lawyers. The international law is unclear. Here's an interesting factoid for you. Because those two lander missions were not NASA missions, they were IM missions. I technically own real estate on the moon. At least right where the lander is. So then the question is, well, okay, but how much more do you do on your porch? Or, no, I don't know. So there are many great questions. And one of the things that there is an alignment going on where there are the Artemis Accords, which is almost 50 countries around the world have signed up with the United States and agreed to the peaceful development and exploration of the moon. One of the things that's unique about the United States is NASA is not military. It's civilian. It doesn't do any military work. China has ILSR, the International Lunar Science Research or something like that. They don't put any of the same statements in about the peaceful development of the moon. And they have Pakistan and Iran and Russia, so not the people that we're real friendly with. That's part of the competition. Why the South Pole? Remember the pictures I showed you where it was really, really dark on the South Pole? The idea is those dark places are so cold, and some of them never, ever, ever see sunlight, that if any water from an asteroid or a comet hits the moon and goes up and falls into those cold spots, they call it a cold trap. And they believe there may be tons and tons and tons of water ice underneath the regolith in those craters. So just like in the Old West, where do you build your towns? Where you have a water source. And so that would be the same. That's why the South Pole is of first interest. But the question of who sets the standards and what are the rules of the road and how do you conduct real estate business? How do you sell goods and services on the moon? There's a lot of work to be done. We like to lead from the West because we want to set those norms in a peaceful way. And that's where we're trying to go as much as we can. Great question. Anybody else? Yes, sir.
On your approach and landing to the moon, you've got your rocket pointed down at the ground at that point. What's with the dust factor with what it's stirring up and you're coming down? What's that screw up?
Yeah, so we use both lasers and cameras on our landing system. And even though the lasers haven't worked great, the cameras have worked really, really well. One of the things you can see in this picture right before we land is you see it's a little bit fuzzy? That's the lunar dust being shot out from the engine. Because there's no air on the moon, it doesn't billow the way it did it just goes straight out. What we do to protect for that though is we know that on this vehicle, for this size engine, that starts at about 30 feet. So what we do is at 30 feet, we turn off the cameras and we basically use land using what's called an accelerometer after that. So we've taken that into account. But it's a big question, it's a big concern, is you've got to know how to deal with that dust. I'm going to tell you, that dust gets moving, and it's moving at about 3 miles a second. So it's like you shot a bullet. And there's a lot of concern when we build the lunar base, how am I going to land and then put equipment out and then come land again nearby because I want to use that equipment and not blast it with the exhaust from the next lander. So we're putting a lot of work across the country in how to build a landing pad, or can I land someplace else and have a big rover, kind of like a tractor, bring the equipment over. So there's a lot of problems with lunar dust. The lunar dust, the regolith, it's almost like ground volcanic glass. And so it's super, super sharp, and it's something we got to worry about. Yes, sir.